Non-homogeneous linear recurrences with constant coefficients. All right, so a non-homogeneous linear recurrence will have the form, I'll write the same stuff I had before, this is degree k, so c1 a n minus 1 plus etc. up to ck a n minus k. If I stop there, this is a homogeneous linear recurrence with constant coefficients. Remember, it's linear because the previous a's, the a's with the lower subscripts, they don't interact with each other. They're separated by addition. So that's linear. Constant coefficients means these c's that are with each of the a's, those are just fixed numbers. It's homogeneous if this is all there is. Non-homogeneous means I can have an extra term out here. Well, I shouldn't say term. An extra thing added out here, which is just a function of n. So called capital F of n. Where capital F of n is it's clearly a function of n, but it is not identically 0. Meaning, it can equal 0 for certain inputs, but it can't be 0 for every input. If it equaled 0 for every input, it doesn't even need to be there. It's just a homogeneous recurrence. Okay, so informally, informally, this f function, this extra thing at the end of our recurrence, this is what I might call a non-homogeneity or an inhomogeneity. All right, so when we're in this situation, we want to figure out how to figure out the general solution to one of these types of recurrences. So let me leave the equation up there and just erase the extra stuff. All right, so let me call this star. Now, once I have this recurrence, and let's not worry about initial conditions just yet. That'll come later. This is just the recurrence relation. Once I have this non-homogeneous recurrence, I can write the same thing, but without the non-homogeneity, without that extra f of n. So I'll call this double star. Double star here is called the associated homogeneous recurrence. Okay, so it's the same recurrence except we just ignore the extra function. All right, so when we're tasked with solving one of these non-homogeneous recurrences, we will also have to consider the corresponding homogeneous recurrence. That'll come into play as we try to solve this. All right, so I recommend you write these two things down and label them with star and double star because I'm going to refer, I don't have any more space to talk about these. I'm going to refer back to star and double star to refer to these two equations. So I'm going to erase. Okay, so here's the theorem. Actually, before I get to this theorem, well, no. We'll put it as part of the theorem. All right, let in P, so that P there, that's not an exponent. It's just a label I'm putting on this. So it's in parentheses here. Let this be any, and the P stands for particular solution to the star equation. So that was the non-homogeneous recurrence. So this is going to be some specific solution to that non-homogeneous recurrence. And let A in H, so the H here is for homogeneous, but I want this to be the general solution to double star. All right, so A and H, that is the full general solution to the homogeneous recurrence that is associated to the non-homogeneous recurrence. Then the general solution to the non-homogeneous recurrence, that star, has the form, or can be written, as the particular solution A n P plus A n H. Okay, so A and P, that is one specific sequence. A and H, that's a general sequence that has like the alpha, the unknown alphas, or the arbitrary alpha coefficients that we don't solve for until we worry about initial conditions. Okay, so I think I'll come back and prove this in a little bit. Well, actually, let me go ahead and prove it now, because I can't really illustrate it yet until we talk about the methods of finding a particular solution. So I'll come back and illustrate it in a little while. Let's prove this. So before I erase, let me just talk about the idea of the proof. It'll just be a shortened sketch of the proof. But the idea is we want to show that once I have any particular solution to star, if I have another particular solution, their difference will be something of the form of the general solution. So in other words, if I have two different particular solutions to the non-homogeneous recurrence, their difference will be a solution to the homogeneous version. So in general, any solution can be written as a particular solution plus some homogeneous solution. And this general homogeneous solution, that represents every possible homogeneous solution, or solution to the homogeneous recurrence. Okay, so let me sketch that. It's not very hard, it's just kind of heavy on the notation. So here's the proof. Suppose we'll call it Bn as a sequence is a solution to the non-homogeneous recurrence. So that was star. Should have labeled them as like star N and star H or something. All right, then we can write. Okay, so hopefully you have the recurrences in front of you. Bn is a solution to star. So that means if I plug Bn into that recurrence, I get a valid equation. So we have Bn equals C1 Bn minus 1 plus C2 Bn minus 2, etc. up until ck bn minus k plus my function, my non-homogeneity function, f of n. So bn has to satisfy star, so if I plug it into star, I still have a valid equation, a valid recurrence. We also have apn is a solution to star. So apn will also satisfy the same recurrence, so I can write it like this. I plug in apn as my sequence to the recurrence, I get this. So now if I subtract this line minus this line, I get bn minus apn equals, I'm just going to do it in one go here. These two terms, this column here has C1 in common, so let me factor out C1. I have C1 times bn minus 1 minus AP in minus 1. That same thing happens in every column. Here I factor out CK, and I have bn minus k minus AP in minus k. But then when I get to the last column, that's just my f of n function. That's the same in both equations. So when I subtract, that cancels. And so what I get here is, if you look at this, if I think of this difference, bn minus apn, as its own sequence, it is satisfying the equation double star. So therefore the sequence bn minus apn satisfies double star, the homogeneous form of the recurrence. So I'm out of space, so let me just say the rest of it in words. That tells us that bn can be written as apn plus this. So I'll write, I guess I will write it. Take it back. bn equals apn plus this thing here, bn minus apn. If I add these together, the apn's cancel, and I get bn. So any solution to the star, to the non-homogeneous recurrence, can be written as that original particular solution apn plus some solution to double star. So this solution to double star is a special case of the general solution ahn. So it's a version of ahn with a specific pair of alpha, or a specific set of alpha values chosen. Okay, so I'm going to call that the end of my proof since I'm out of space and we've basically done it all. All right. So that means that the theorem tells us then that to solve a non-homogeneous recurrence, we basically have two steps. We have to come up with a particular solution, any particular solution, and we have to find the general solution to the homogeneous version. So let's talk a little bit about finding particular solutions, and then we'll do one in completion. So how do we find APN? Okay, so the bad news is there's no general method. It basically depends on how complicated your f of n function is. So I can make up all kinds of things for f of n, all kinds of horrible functions for that, and most of them that I make up, we would not be able to come up with a particular solution. Okay, but for specific types of f of n functions, So specific kinds of functions that are that non-homogeneity. We can make an educated guess and then fill in the blanks with a little bit of algebra. Okay, so let's do a simple example. All right. All right, so suppose, let's start with a recurrence. An equals 3an minus 1 plus 4an minus 2. So that's the homogeneous part. Now I need a non-homogeneity. Let's do 2 to the n power. So f of n, in this case, is 2 to the n. Okay, so our thought process is, our guess for APN, we want to essentially match the kind of function f of n is. Now, it won't be the same function, it'll just be the same type of function with some extra coefficient, or extra coefficients in general. Okay, so what I mean by that is, if I were to describe in words what this is an exponential function with base 2. So let's start with an exponential function with base 2, so the same function, 2 to the n, but it's not just going to be the exact same function. That would be ridiculous. So let's just naively say, well, let's suppose it's that same function, but let's stick an extra coefficient with it. So an a, where a is some number. Now, we're not saying, it's not true, that anything of this form will work. We're going to say that something of this form will work. So for some specific a value, capital A value, this function will work, this sequence will work as a solution. Okay, so it's up to us to find a. So now solve for a, capital A. Okay, so what that means is we're going to assume that this sequence satisfies that recurrence. So let's plug in this specific formula in place of little a-n's. So we're going to plug in n minus 1, and n minus 2 into this sequence. So my equation, let me call it star. Star becomes well, an is I'm just plugging in APN in place of an. We get a times 2 to the n equals 3 times a times 2 to the n minus 1 plus 4 times a times 2 to the n minus 2, and then plus 2 to the n. All right, so we now have an equation with an unknown a, and it's supposed to be true for every n value, every whole number n value. So let's try to get rid of the n. So what I want to do is divide out as many 2's as I can. So if you look at this, every single term in this equation now, every term has a power of 2. The one with the fewest power of 2 is here, 2 to the n minus 2. So I'm going to divide out 2 to the n minus 2. So this is just describing what I'm doing here. So if I do that, I'm going to be left with 2 squared here. So that'll be a times 2 squared equals 3 times a. This divided by 2 to the n minus 2. I'll still have 1 2 left over. Here I'll have 4a, and all my 2's are gone, plus 2 squared. Okay, so that tells us 4a equals 6a plus 4a plus 4. That's a simple algebra equation. Now we can solve that for a. So if I subtract 4a and 6a, I get negative 6a equals 4. So a equals 4 over negative 6, which is negative 2/3. So from that, we have our particular solution. So let me copy it here. APN equals negative 2/3 times 2 to the n. Right, so in a sense, we're approximately halfway done with the recurrence. We found the particular solution for this non-homogeneous recurrence, but now we need the general homogeneous solution so that we can get the general solution to this. So double star for this example, the homogeneous recurrence would be the same thing but without the 2 to the n. So an equals 3an minus 1 plus 4an minus 2, and that's it. So then I would need my characteristic equation, which, abbreviating this example, this is going to be r squared minus 3r minus 4 equals 0, which factors as r minus 4 and r plus 1. So my roots are 4 and minus 1. So from last time, that gives us our homogeneous solution. AHN is going to be of the form alpha 1 times one of these roots to the nth power plus alpha 2 times the other of the two roots to the nth power. Okay, so now let me write the general solution then. Our general solution to the non-homogeneous would be AN equals this plus this. Negative 2/3. Let me put parentheses, it looks better. Times 2 to the n plus alpha 1 times 4 to the n plus alpha 2 times negative 1 to the n. So APN plus AHN. Right. So then, this is the general solution. If we had a set of initial conditions, like A0 equals 5 and A1 equals 7 or whatever, then we use those two initial conditions, plug in the n values, and solve for alpha 1 and alpha 2 in the resulting system. Okay, so it's the same idea that we did for the initial value problems for the homogeneous recurrences. It's just a little bit more complicated because we've got these extra functions involved. But it's not really any more difficult in the scheme of things. All right, so for now, let's concentrate on talking about other forms that the non-homogeneity function can take and how to guess the particular solution. So let's do another straightforward example. All right, so let's do the non-homogeneous part first. AN equals AN minus 1 plus 6 AN minus 2 and then plus 3n plus 4. So our f of n here, the extra part that does not involve a, is 3n plus 4. So we look at that type, look at that function, and identify what type it is. And in this case, we look at this and say, this is a degree 1 polynomial. Or a linear function in this case. So our guess for APN should be the same type. So it's not going to be the same linear function, but it's going to be the same degree polynomial. So we'd say it's a capital AN plus B for some A and B. Yeah, so I made an aesthetic mistake last time when I was using capital letters for the unknown, the coefficients in the general solution for a more complicated homogeneous solution recurrence. I'll try not to do that again. I want to use Greek letters for my arbitrary coefficients in the general solution. I want to use capital letters for my guess coefficients for my APNs. It doesn't really matter. It's just to help us keep them straight when we're working these things through. All right. So this is my guess for APN. So then just like before, once we guess the form, just with these unknown coefficients, we're going to plug this function into the recurrence and then try to solve for A and B. So AN becomes AN plus B. AN minus 1 becomes A times n minus 1 plus B. Then I've got plus 6. AN minus 2 would be A times n minus 2 plus B. And then plus 3n plus 4, that's just itself. All right, so then I need to solve for A and B. Now the thorough way of doing this would be multiply everything out, and then get all the like terms together and match the like terms on each side of the equation. Yeah, I say that. I guess that's probably the most straightforward way. So let's just do it that way. So we'll have AN minus 1 or minus A, distributing the A, plus B plus 6AN, then 6A times negative 2 will be minus 12A, 6 times B, and then plus 3n plus 4. Okay, so here's where I'm going to take a shortcut. Well, what I consider a shortcut. Opinions may vary. I want to match coefficients, so let's just look at the things that have n's. Well, on this side I've got AN, so I get A. On this side I have AN, 6AN, and 3N. So A plus 6A plus 3. So that's 7A plus 3. So then we can solve that equation for A. Negative 6A equals 3. So A equals negative 1/2. So let's erase that. Let me preserve what A is here. A is negative 1/2. Now I need to know what B is. So rather than look at the parts that have an N, I look at the terms that don't have an N. And just match those. So B equals negative A plus B minus 12A plus 6b plus 4. So we want these two polynomials, these two sides of a polynomial equation to be equal, so the coefficients on each power of the variable have to be the same. So if the n coefficients have to be the same, the constant parts have to be the same. So now let's consolidate this. B equals negative a minus 12a is negative 13a. And I've got 7b plus 4. So let's subtract 7b from both sides. So negative 6b equals negative 13a plus 4. But now we know what a is. It's negative 1/2. So that's actually positive 13 over 2 plus 4. 4 is 8 over 2, so that's 21 over 2. Now I want to divide by negative 6. So b is negative 21 over 12, or negative 7 over 4. Okay, so it can get a little bit messy, but it's a straightforward algebra problem to solve for the unknown coefficients on these things. All right, so after all that work, our particular solution looks like negative 1/2 n minus 7 over 4. All right, so let's do the homogeneous part now, just to complete it. So the homogeneous part would be, the homogeneous recurrence would be an equals an minus 1 plus 6an minus 2. So our characteristic equation would be r squared minus r minus 6 equals 0, which has roots 3 and negative 2. So AHN would be alpha 1 times 3 to the n plus alpha 2 times negative 2 to the n. Okay. So let's write the full solution. Let me give myself some more space here. The general solution would be APN plus AHN. So AN equals negative 1/2 n minus 7 over 4 plus that stuff. Okay, so then just to do it at least once, let's complete this problem. So say this was all part A. Find the general solution of this recurrence relation. And part B, now find a specific solution where A0 equals, let me try to choose carefully here. I don't know if I can do it. A0 equals 1, and A1, let me do it here. A1 equals 2. So we want these initial conditions. We have this recurrence with these two initial conditions. So once we have the general solution, the particular part of it fixed. That's non-negotiable. There's no ambiguity about its coefficients at this point. We've already figured those out, what they have to be. The freedom comes from the alphas and the general in the homogeneous part. So what I have to do is I have two alphas that are unknown. To get a unique solution, that means I have to have two initial values in my recurrence. If I just gave you one of them, then I wouldn't have a unique solution. I'd be able to find some relationship between these two alphas, but I wouldn't be able to solve them completely. But in any case, if I want to account for these initial conditions, I'm going to plug in the subscripts for n and write down the resulting equations. So when n is 0, I will get A0 is supposed to be 1, so the left side is 1. The right side is going to be, when this n is 0, that disappears. I have negative 7 over 4 plus alpha 1 times 3 to the 0 would be alpha 1 plus alpha 2 times negative 2 to the 0, that would be alpha 2. So alpha, let me rewrite it here. Alpha 1 plus alpha 2 will be 1 plus 7 over 4, that'll be 11 over 4. So there's one equation. Now I plug in n equals 1. I'm supposed to get 2 as my value. If I plug in 1 on this side, I get something worse. So I'll get negative 1/2 minus 7 over 4 plus, when I plug in 1, I get 3 alpha 1 and minus 2 alpha 2. So what's this? This is going to be negative 2 fourths, so that's minus 9 fourths. Add that over, I'll get, oh boy, it's 8 over 4, so 17 over 4. Right, so after all that, now I've got this system of two equations that I'm not really wanting to solve on this whiteboard in my diminishing corner here. I guess it's not too bad. Or is it? An exercise. So solve that for alpha 1 and alpha 2. It's just a simple system of equations, but I didn't make it up with neatness in mind. All right. So let me take a second to think about what I want to do next. All right, yes, I think the best thing to do, since we're getting close to 40 minutes on this one, the next thing that we need to discuss, we're not done with this because I've only done two very basic examples with non-homogeneous parts. So for those two very specific things, we have a method. But I haven't really given you the general rule for how to make these guesses. I made two very basic examples and told you what a reasonable guess was. So what I want to do next is tell you what the general rule is. So first off, what types of non-homogeneity functions can we do this with? So what is the basic form of an f of n that we know how to handle? And then once we know the form, how do we make the guess? Because it can get a little bit more complicated than just a single polynomial function or a single exponential function. Okay, so we'll do the theorem in the next video, and then we'll do lots of examples for constructing them. All right, so let me stop.